All right, thank you very much, Flora. First of all, wanted to tell you I'm saddened that the two lead authors, my students, could not make it due to visa issues, so I'm here to present on their behalf, but I also have Stefany Cruz, I believe, is here. Yay, Stefany, all right. Would like to, I'm really excited to talk to you about SmokeMon, or some people would love that I call it SmokeMon. You might have seen some SmokeMon Pokemons out there. But today I'm going to be talking to you about smoking, so let's get into it. We know that smoking is the leading cause of preventable disease worldwide. Still, almost about a quarter of adults smoke. In the US, we've made quite a bit of strides in this area, but still 20% of deaths are caused by smoking. Millions of adults still smoke, and it's taking a toll on our healthcare system. Now, we do know that assisting patients in smoking cessation is still an important primary care task, and medication is still not where we want it to be in terms of its effectiveness. And so when we talk to tobacco treatment providers, we notice that they want to understand smoking behavior a little bit better in order to personalize their treatments. And so we know that existing measures, self-report measures, are, there's fraught with response bias, limited details, and I'll talk about limited details in a while. There's also our ability to obtain, serum cotinine assays or dried blood spots to actually get at nicotine exposure in more detail, but still this is burdensome, non-real time. Wearables, which is sort of our community's focus, and there's been a lot of people here in this community that have focused on detecting smoking events, right, and being able to characterize them. They're passive, continuous, low burden, real time, but at the same time we know they still generate a lot of false positives in the real world, and there's still limited detail. And so we came across these clinical research support systems, this CREST pocket, that allows us to get at real, detailed smoking behavior, right, non-invasively and in real time. So let's talk about this. What's amazing about it is it measures something called smoking topography, which is fine-grained measurements of smoking events, right, and they really tell us how people smoke. And what it is it's this respiratory flow meter. A person puts a cigarette on one end and then smokes from the other end. And we're able to measure interesting markers like puff volume, number of puffs, interpuff duration, puff duration, smoking duration. All these factors or metrics are what, combined are what we refer to as smoking topography. And there's a lot of great, interesting associations with smoking topography and nicotine dependence. So the more, right, the greater the puff duration, the greater the number of puffs, the greater the smoking duration, the greater the motivational drive to smoke, right, the greater the nicotine dependence. There's also a lot of associations with carbon monoxide measurement and also predicting potentially post-treatment abstinence. But still, this device must be, you have to smoke through this device, right? And so it reduces, it's still bulky, even though they've miniaturized it quite a bit. It reduces the realism of smoking events, right? Obscuring really that natural behavior. So we designed SmokeMon, a wearable necklace using thermal sensing, right, to measure smoking topography unobtrusively, as Flora mentioned, a key term, right? We reduced the form factor quite a bit. And what's interesting here is with this thermal sensor array, we can see here the thermal camera as the person takes a puff, we can actually see the heat signature of the cigarette quite clearly. And so here, what this allows us to do, it rests on the chest, it orients itself, the thermal lens orients itself upward, and we're able to capture the head, hands, as well as the cigarette tip. But we're also able to capture a lot of other activities that the person's also performing, which is really interesting from a thermal sensing perspective. Now here we see a live feed of the maximum temperature of the frame, a time series, the max temp of each frame. And here we can see how we're able to capture the interpuff interval, puff volume, number of puffs, as well as smoking duration, right? And these are really interesting. This showed some promise in our ability to use this as a sensor. We tested different types of sensors, the FLIR camera, which has a high resolution, but then again, there's the cost of power as well, the grid eye, lower resolution, but much better when it comes to power. And so we took the middle of the road and we went with the MLX, which gives us, fine enough resolution so that if someone was to smoke to the side, we can still capture it. And so here we see SmokeMon prototype. We have the top enclosure, we have the main board, which is a Cortex M4 based Apollo 3 microcontroller. There's also a mounted breakout board with a thermal sensor that allows us to adjust the orientation based on body type to make sure that we orient it properly. And there's also a magnet pad. There's the 3D case is nice because it allows us to personalize it based on what people would like to wear. We also did some battery testing, right? And there's more detail in the paper, but SmokeMon provides 19 hours of battery lifetime. So it allows us to capture smoking behavior throughout the entire day. Now here's the deep learning pipeline. And what we do is we start with using the thermal heat to actually capture candidate smoking events. We then deploy a MobileNet V2, which is lightweight, allows us to run it on device, right, and apply different data augmentation techniques to allow us to detect puff events. We then cluster puffs together and extract the maximum temperature curve and build a regression model that allows us to estimate puff volume. We did a study both in lab and in the wild. In lab, we used the Crest Pocket to compare against puff volume and Crest Pocket as a gold standard. And then in the wild, we actually had them self-report their smoking events, and we had them actually also, we also labeled the puff behavior detail post-study. Now, there's much more detail in terms of the results in the paper. However, in lab, we were able to obtain a 90% F1 score with leave one participant out and about 80% in wild. We show a strong correlation between the puff volume that we estimate with the regression model and that compared to that of the Crest Pocket. And we asked several questions about comfort, bystander reactions, and attitudes about sharing their data. There's a lot in the paper there for you to read, but interestingly here we see that they weren't really concerned about sharing. We got more not at all concerned about sharing their data, which was great from a privacy concerning perspective. In our future work, we're really excited to look at how smoking topography, pre-quit and post-quit, can help us predict, right, what causes a person to relapse, and also maybe detect that slip before it turns into a full-blown relapse. So we can try to intervene in time and design these personalized interventions. We're also looking at connecting this to biomarkers and biological responses through dried blood spots, so interesting work there. We're working with the Respiratory Health Association in their Courage to Quit program as well. So, my final slide, SmokeMon is wonderful, please continue to read the paper. We've got a lot of media attention, there's a lot there too, and a little shout out to my lab, we're hiring, and that's it. Thank you very much.
We can take one question while there's a switch. Is there any question from the room? No? Otherwise, yes, please.
Hi, great talk. I'm Harshit from Syracuse University. Having worked with thermal cameras, I have seen that there is a latency issues, also issues with like shadows. So how do you deal with those issues while processing the thermal images? Shadows and the resolution itself.
Hopefully you heard some of that. Basically, what we do is we use the thermal heat to try, if we can actually get at least 1 or 2 puffs out of the full event, then we've got like a candidate smoking event. And then from there, our deep learning model is not only looking at detecting the heat, but actually the gesture. And this is where our data augmentation methods were really critical. So I ask you to look at that as well, because what we do is we remove the heat signature, so it can actually still detect the smoking gesture, even if it doesn't see the actual heat. You're welcome.
Thank you so much, Nabil. Let's give it a hand.